Hello, everyone. This is Group 17, and my name is Kagolo Fridaus. And we're going to take you through our machine learning project. And our title is Multi-Strategy Psychological Signal Processing for Intensive Healthcare using ECG Knowledge Distillation. And this study explores how we can improve ECG analysis in intensive healthcare settings using advanced machine learning. And our content, these slides are going to include our introduction, the related works, the problem statement, research questions and objectives, research contributions, our methodology, dataset description, results of the experimental and simulation, conclusions, anticipated limitations and counter interaction, plan, conferences, references, and acknowledgements. Well, our background and introduction. First, ECG signal processing is essential for cardiovascular health monitoring, but it faces challenges like noise, contamination, complexity, and real-time analysis. Traditional methods rely on visual inspection, which is subjective and time-consuming. Our research focuses on integrating deep learning and knowledge distillation to improve ECG analysis for intensive health care. And our related works and recent trends. Existing research has applied deep learning techniques such as CNNs and RNNs to ECG classification. Hybrid models combining CNNs and LSTMs have shown promise. Well, knowledge distillation has also been explored to create efficient models for real-time ECG analysis. However, challenges like computational complexity and motor interpretability still exist. Well, our literature review. Insights from existing research. Our dataset challenges. We had severe class imbalances in datasets, which affected our model performance. The interpretability. There was need for explainable AI to build trust among healthcare professionals, focus on developing models that provide clear insights into decision-making processes. And our future research, we intend to enhance transfer learning techniques, refining hybrid deep learning frameworks for robust and efficient ECG analysis. And the problem statement, well, cardiovascular diseases, the leading cause of death worldwide, accounting for nearly 18 million deaths annually. Well, ECG signals provide a non-invasive method for monitoring heart health, but deep learning models require high computational power and are often black box models, making them difficult to interpret in practice. Well, our computational problem, we had deep learning limitations. Well, this requires substantial computational resources and large volumes of labeled data for training, and also model interpretability, where we had a significant barrier to clinical adoption. Well, our research questions and objectives, we had questions before we premiered our research. We had questions. How can we enhance ECG signal processing in intensive healthcare? How can legislation enhance ECG signal processing in intensive healthcare? What pre-processing techniques improve ECG signal quality? Can psychological signal processing aid in detecting stress-related cardiovascular issues? Well, our objectives included determine optimal pre-processing techniques and a model to determine a model and a lightweight ECG classification system. Well, our objectives include developing a lightweight ECG classification system, optimizing pre-processing, and evaluating performance. Well, our research contributions. We developed a robust ECG pre-processing pipeline, created a lightweight classification model, using knowledge distillation and integrated psychological signal processing by analyzing heart rate variability. Our system outperforms state-of-the-art methods in accuracy and efficiency. Well, this is our methodology diagram. It precisely describes our steps that we followed in building our project. Well, our methodology, this approach follows these steps. We have data collection, the pre-processing, speech extraction, distillation, model training, evaluation, and deployment. It ensures a streamlined and effective pipeline for ECG signal analysis. We'll go to our dataset description. Well, we use the MIT-BIH rhythm database, which contains ECG recordings from 47 subjects. It includes a mix of patients and outpatient recordings and captures various types of arrhythmias, making it a valuable resource for training and testing our models. Well, it has subsets. Our subset 1 had 23 recordings, and subset 2 had 25 recordings. Well, these recordings were selected at random from outpatients and inpatients from Boston's Beth Israel Hospital. Well, my colleague will take you through our visualizations.
Book 17, my name is Charles. This is our visualization, and then we see three plots representing ECG or electrocardiogram signal transmissions. And one is the original ECG, that one at the top, and this is a clean, undistorted ECG signal before transmission, and it shows typical periodic waveform of a heartbeat with clear peaks, which represent different cardiac cycles, and that one represents a correctly restored cycle. And with the second one is the one transmitted over a communication channel, such as a wireless or wired media, and it appears noisy. As you see, they are compacted, the signals are compacted. So it is due to interference and signal degradation. So the third, it is a signal after applying some form of signal processing, where you will see the left part of the signal is the one restored correctly, whereas the other part is the one that is not well visible or degraded. Basically, the plot you see, it is a box plot of the ML double I and the V5 plot. Basically, the ML double I, it is a modified lead 2. The V5, it is a pre-coded lead V5. And the box plot basically represents 50% of the data middle, where the first quartile, where you shall see the first quartile to the third quartile. And the horizontal line, as you see, inside the box is a medium, and it indicates the central value of the ECG amplitude, whereas the width of the box suggests the variability of the ECG amplitude data. The whiskers extended from Q1 to the minimum, and from Q3, which is the quartile 1 and the quartile 3, or the upper and the lower and upper quartile respectively. They show the range within 1.5 times the quartile range. And basically, these are the algorithms used, where we shall see the CN in the configuration unit work. And the first step, we shall initialize the model. And second, we shall extract features. Then we train the model and we predict arrhythmia. The model will predict arrhythmia. So the other is the contrastive learning. As you see the steps we have, we initialize the model, then we generate the positive and negative pairs in our model. Within that, we generate those pairs so that we differentiate between the two. Then we train the model, and then we classify them, because it basically classifies. The other is a somewhat smooth electrocardiogram for patient 100. Basically, this represents the ECG signal for that patient, and it is a medical test report for electrical activity of the heart over a given period of time. Yeah, with it, it has the amplitude that is on the y-axis, as you see. This axis represents the amplitude of the electrical signal, and typically it is measured in millivolts every. And peaks in the amplitude correspond to specific electrical events, yeah, in the heart, such as the P wave, KRS complex, and T wave. And the time on the horizontal, it is usually measured in seconds, and it shows how the heart's electrical activity. The figure shows how the heart's electrical activity changes with time. So we have a PSD, a visualization of a PSD, a power spectral density. It has a y-axis that represents the power, and it represents power of the signal at each frequency. The power values are often plotted on a logarithmic scale, indicated by the labels, and this helps to visualize the wide range of power levels. Then we have the frequency on the x-axis, and it represents the frequency of the signal. This plot goes from 0 Hz to 175 Hz, and the power spectral density describes how the power of the signal is distributed across different frequencies. And with this here, we show classify basically the train versus the validation accuracy, where you shall see the train that is orange, or the validation accuracy in orange, and the train accuracy in blue. So the train accuracy is as low as 0.5, and the validation accuracy is as high as 0.5 to 5. So with that, the train validation accuracy appears to be a set of plots used to evaluate the performance of a machine learning model during training. And we have the train versus the validation accuracy. Basically, we have accuracy, the vertical axis, which is the proportion of correctly classified instances, the epochs. These are iterations over the entire data set. Within, we have the conclusion for our project, and the limitation. Basically, we were limited by generalization to diverse population, model interpretability, and real-world deployment. In our future works, we are aiming at generalization of our model, focus on more performances in those rare conditions. Then we shall aim on model integration, adding more features to it. Then interpretability, increasing on its accuracy, basically, so that it's able to interpret data easily. In future work, we are recommended so that we aim at collaborative research to engage in disciplinary collaborations with clinicians and engineers to ensure practical and clinical advancements. Then we have data augmentation, where we shall utilize synthetic data generalization technique to address the data set imbalances. Then even continuous learning to adapt our models to new data and emerging trends in biodiversity. Those are our acknowledgements, and that's all for our presentation of our paper. Thank you.